Welcome to the Deep Dive. You've shared some really fascinating technical papers with us, and our mission today is to really get to the heart of how reliable these DFIG wind turbines actually are.
Right, the doubly fed induction generators.
Exactly. We'll be focusing on, electrical and current signature analysis, ESA and MCSA, and how these methods basically act as early warning systems for these, crucial energy producers.
Exactly. Think of this as your fast track, sort of, to understanding a vital aspect of keeping that wind energy flowing. We're aiming not to get too bogged down in the super technical weeds,
Okay.
But we do want to equip you with the core knowledge, where these turbines tend to run into trouble, and crucially, how we can spot those issues before they cause major disruptions and major expense.
Right. The expense part is huge. So from these technical papers you've gone through, what are the key things we really need to understand about keeping these massive things turning? What's our main goal here?
I'd say our overarching goal is to pinpoint the most common weak spots, the vulnerabilities in these DFIG turbines, and then to really see how ESA and MCSA work as these, sophisticated detectives.
Detectives, I like that.
Yeah, interpreting the electrical language of the turbine to flag potential problems really early on. We'll explore how these techniques are just instrumental in maximizing turbine uptime and keeping those operational costs manageable.
Okay, let's get into it then. When we talk about DFIG wind turbines, whether they're, onshore or out there offshore, what are the main things that tend to go wrong? What impacts their reliability most?
Well, reliability is absolutely paramount, isn't it? It directly hits how much energy they generate and the bottom line, the cost of running them. The papers definitely highlight several key areas of concern.
Such as?
Within the generator itself, we often see issues with bearings, stator wedges, and also rotor wirings. It's interesting, actually.
Yeah.
Earlier research, back in 2011, pointed to generator bearings as a primary culprit, often because of these stray electrical currents,
Right, I remember hearing about that.
But by 2018, the data showed a pretty significant increase in rotor wiring failures, up to maybe 20%. While bearing problems, thankfully, had become a bit less frequent, down to about 25%, probably because insulated bearings became more common, especially in those smaller onshore turbines.
Rotor wirings. Okay, that sounds pretty critical. What about the other big moving parts? The gearbox.
The gearbox. Yes, that's another really significant area. Bearing failures there are very often linked to electrical discharge.
Again with the electrical discharge.
Again, yeah. And the gears themselves, they can suffer damage too. Plus, lubrication issues, even tiny misalignments can cause big problems. The numbers are quite stark, actually. Electrical discharge seems implicated in something like 76% of gearbox bearing damage.
Wow, 76%.
And over 17% of gear failures. Then you've got the main bearings, the huge ones supporting the blades and the hub. Lubrication and, yes, electrical discharge again are the major culprits. Over 60% of their failures.
60%. That's huge.
It is. And even the blades themselves, misalignment, unbalance. MCSA can actually pick up on that too, surprisingly.
That's quite a list of potential headaches.
Yeah.
So roughly, how often are we talking about replacing these things over the turbine's life?
Well, over a typical 25-year operational life, you could reasonably expect to replace maybe one blade, one main bearing, one generator, and possibly even 2 gearboxes.
2 gearboxes. Ouch.
Yeah. And it's generally agreed that offshore turbines, facing those harsher conditions, they tend to see these failures a bit more frequently. So for anyone managing a wind farm, the big picture here is significant long-term costs for replacements, which really underlines why early detection is so valuable.
That sounds like it could get very, very expensive fast. Are these failure patterns specific to certain manufacturers? Or maybe just certain places?
What's really fascinating and maybe a bit concerning is that the main types of defects seem remarkably consistent across different turbine designs, different manufacturers, all over the world. Yeah, whether you're looking at turbines in the US, Canada, Mexico, Brazil, across Asia, Europe, the Middle East, the fundamental reliability challenges are surprisingly similar.
So it's not just one bad design or batch.
It suggests the core stresses, the environmental factors, they're universal challenges the whole industry is grappling with, no matter who built the machine or where it is.
Okay, that makes sense. If the problems are widespread, you need robust ways to find them. Which brings us back to ESA and MCSA.
Exactly. Which brings us to electrical and current signature analysis.
So let's dive into that. What are the basic principles? How do they actually work?
Okay, so think of ESA and MCSA as these really sophisticated diagnostic tools. They're essentially listening to the subtle electrical signals coming from the wind turbine.
Listening how?
Well, ESA analyzes both the voltage and the current. MCSA, on the other hand, just focuses on the current. But the core idea is the same. As parts inside the turbine start to wear out or develop faults, they create tiny, almost imperceptible changes in these electrical signals. And by examining the frequency content of these signals, what we call spectral data, we can identify these very early warning signs. It's like, imagine the electrical signal as a musical chord. Spectral analysis breaks it down into the individual notes.
Right.
And each failing component adds its own unique, slightly off-key note to this electrical chord.
So in a way, the turbine is constantly telling us if it's feeling a bit under the weather.
Precisely. And what's really quite ingenious about it is that the air gap within the generator acts like a natural sensor, a transducer.
The air gap, how does that work?
It means we can monitor not just the generator itself, but the health of the entire system, from the blades down through the gearbox, the whole powertrain. It's like having this central listening post for the whole mechanical setup.
That's pretty clever physics at work there. How long have these techniques actually been around? Have they changed much?
Oh, they aren't brand new, not at all. ESA was initially developed back in the mid-'80s, mainly for nuclear power plants, for monitoring motor-operated valves.
Okay.
Yeah. And around the same time, MCSA emerged over in Scotland, initially focused on detecting faults in the rotating parts, the rotors of electric machines. Both became commercially available, early 90s.
A few decades, though.
Right. And since then, the field has seen huge advancements, machine learning, AI kicking in after 2015, that led to systems that could automatically learn and spot fault patterns.
The AI wave.
Exactly. More recently, maybe around 2021, we started seeing hybrid AI systems. These combine the knowledge of human experts with the raw data crunching power of AI. And now, it's even getting common for companies making protective relays or VFDs, variable frequency drives, to build ESA MCSA capabilities right into their products.
So it's moving from specialized kit to being integrated into standard equipment. What does a typical setup actually look like inside a turbine?
A standard ESA setup usually means measuring voltage and current on all three electrical phases. That raw data then gets fed into specialized hardware and software for the analysis. MCSA is similar, but it might only need current measurements from 1, 2, or all 3 phases.
Okay. And you mentioned spectral resolution earlier. Why is having good resolution so vital here?
Resolution. Think of it as the ability to tell the difference between very similar frequencies in that electrical signal. It's absolutely crucial.
Why is that?
Because different types of faults often generate signatures, those off-key notes we talked about, at frequencies that aren't incredibly close to each other. If your resolution isn't sharp enough, it's like those signals just blur together, makes it really hard to pinpoint the specific problem.
So you might know something's wrong, but not exactly what.
Precisely. The papers we looked at mentioned systems with resolutions down to 0.02 hertz, even one at 0.009 hertz, which is really impressive. Achieving that often means collecting data over a longer time period, maybe a minute or two. This fine-grained detail is what lets you accurately diagnose complex issues. Without it,
yeah, it's like trying to pick out one voice in a really noisy crowd. Everything just blends. Right. You need to hear those faint whispers of a problem amidst all the normal electrical hum. Now, you also mentioned the line frequency being a carrier frequency with message frequencies. Can you break that down a bit more?
Yeah, that's a really helpful analogy, I think. The main electrical frequency from the grid, usually 50 or 60 hertz, depending where you are, that acts like a radio station's main broadcast signal. The carrier frequency.
Okay, the main signal.
Right. Now, when a fault starts developing in the turbine, it generates its own unique little error signals. These are the message frequencies.
Revolt signal.
Exactly. These message frequencies then essentially piggyback on top of that main signal. And this creates what we see in the frequency spectrum as sidebands. They look like smaller peaks popping up around the mainline frequency peak, usually at frequencies of the carrier plus or minus the message frequency, so FDC, LFM.
And the size of those peaks matters.
Absolutely. The size or amplitude of those sideband peaks, we often measure it in decibels. dB gives us a really good indication of how severe the fault is. Think of decibels as just a way to measure the strength of these fault signals. A higher dB number generally means a louder warning sign, something getting more serious.
That analogy really helps make it clearer. And this analysis, it can tell us about issues both radially, like inside the generator itself, and torsionally, affecting the whole rotating powertrain.
Precisely. You can think of the stationary parts, like the stator and the rotating parts, the rotor, as the radial components.
Yep.
And then the shaft, the gearbox, the whole system transmitting torque, the powertrain, those are the torsional components. Problems in either will leave their distinct fingerprints in those electrical signals, which can be mathematically modeled.
Does anything get lost in transmission, like through the gearbox?
Well, there might be tiny energy losses in things like couplings and the gearbox itself, but the research suggests these are usually pretty minimal. They don't typically distort the main fault signatures we're trying to spot.
Okay, so with that foundation laid on ESA MCSA, let's get into some real-world examples from the papers. How do specific defects actually show up in the data? Let's start with those rotor Y ring defects you said were becoming more common.
Absolutely. Y-ring fractures, they're a critical generator issue. They can lead to complete failure pretty quickly, sometimes just hours after the final clear detection signal appears.
Hours? Wow.
Yeah, it shows up as a current oscillation at twice the slip frequency. We call that the pole pass frequency, or PPF. The root cause, usually a break in the hoop connecting the winding center, or maybe the connecting tabs or leads break off.
That sounds bad.
It is. But the good news is, if we can catch this early, before a second catastrophic fracture happens, these can often be repaired right up there in the nacelle.
Ah, an up-tower repair.
Exactly, which saves a massive amount of money. We're talking maybe $10,000 for an up-tower repair versus $150,000 or more for a full generator replacement if it fails completely.
Huge difference. So what's the very first sign? What does ESA MCSA pick up early on?
The initial sign of a Y-ring starting to fracture is an imbalance in the rotor's magnetic field. This imbalance effectively mimics a condition we call dynamic eccentricity.
Dynamic eccentricity.
Yeah, it's like the rotor is magnetically spinning slightly off-center within the air gap. So we look for that pole pass frequency, the PSIF, which you calculate using the number of generator poles, the main frequency, and the turbine speed. And we also look for the dynamic eccentricity frequencies, which involve the number of rotor bars or slots as well.
Okay.
What's important here is that the strength, the amplitude of these peaks doesn't really change with turbine load, but their exact position on the frequency graph will shift as the turbine's operating speed changes.
Right, because the slip changes. Can you give us a quick example? What might those frequencies look like?
Sure. Let's say you have a turbine running at 1215 RPM, which is about 20.25 hertz rotational speed. If it's a 6-pole generator on a 60 hertz grid, the pole pass frequency would be around 1.5 hertz. And the dynamic eccentricity frequencies, well, if the rotor has 54 slots, those would show up in a broader range, maybe from around 770 hertz up to 1400 hertz or so, depending on the exact conditions.
Wait, that makes it a bit more concrete. What about stator wedge loss? The sources mention that too.
Right, stator wedges. Most wind turbine generators use ferrous, sort of metallic wedges in the stator slots. Their main job is to reduce unwanted harmonic frequencies in the air gap. Those can cause losses and noise.
So they smooth things out.
Exactly. Now, when these wedges get loose or even fall out completely, it creates a very distinct signature in the ESA MCSA data. We look for peaks at specific frequencies calculated from the number of stator slots, the rotor speed, and the line frequency. Any signal there, any dB level popping up above the normal background noise indicates a potential issue.
And a higher signal means a bigger problem.
Generally, yes, a higher dB level could mean more wedges are loose, or maybe just one is very loose, or it could indicate more significant movement of the electrical coils within the stator slots.
What's the risk if these wedges come loose? What can happen?
Well, the big danger is that a loose or ejected wedge can get caught in that very narrow air gap between the stator and the rotor.
Ouch.
Yeah. If that happens, it can cause serious damage to the stator winding insulation, potentially leading to a short circuit or a failure to ground, a really serious, costly event. We also look for a related signature that indicates stress on the stator winding itself.
Winding stress.
Right. It can be a precursor to insulation breakdown, sparking, or something called partial discharge. All bad news, potentially leading to a wind-into-ground fault or a short between windings. If we see both the wedge loss signature and this winding stress signature together, that usually signals a need for immediate attention.
And again, catching it early means.
Yeah. Catching wedge issues early often allows for an up-tower repair. Maybe re-wedging the stator. Again, far, far cheaper than swapping out the whole generator later.
Makes sense. Okay, moving along the powertrain, main bearing defects. We heard electrical discharge is a huge factor there too.
That's right. The main bearings are absolutely critical. They support the immense weight of the blades in the hub, and they keep that main shaft perfectly aligned. And yes, over 60% of main bearing failures are attributed to damage caused by stray electrical currents discharging right through them.
60% again. So how do defects show up here? The main shaft turns much slower, right?
It does, much slower, typically less than 20 RPM. So the specific frequencies that indicate a defect are related to that slow rotational speed, combined with specific multipliers unique to the different parts of the bearing, the inner race, the outer race, the cage holding the rollers, and the rollers themselves.
So how does that slow mechanical frequency show up in the electrical data from ESA MCSA?
Good question. Because the shaft turns so much slower than the main electrical frequency, like 50 or 60 hertz, the bearing defect signatures appear as sidebands around that main frequency.
Sidebands again?
Exactly. For example, let's say a bearing's outer race defect has a characteristic multiplier of, say, 0.9661 times the shaft speed in hertz. If the shaft is turning at 19 RPM, that's only about 0.317 hertz. We'd look for small peaks in the spectrum around 60 hertz, plus or minus about 0.306 hertz.
So very close to 60 hertz.
Extremely close,
Yeah.
like 59.7 hertz and 60.3 hertz, roughly. This is where that high spectral resolution we talked about becomes absolutely vital. These frequencies can be incredibly close together, easily missed or misidentified with lower resolution equipment.
Right. And what else can those signatures tell you?
Interestingly, an outer race signature might not even be a crack yet. It could just indicate poor lubrication. Maybe the rollers are literally bumping over areas of dried out grease. Still something you want to know about.
Definitely. And the cost implication here.
Replacing a main bearing is a massive, massive job. You usually have to remove the blades and the entire hub. Costs can easily run upwards of $500,000. So again, early detection is just incredibly valuable.
Wow. Okay. The sources also really emphasize insulation defects. How good is ESA MCSA at catching those kinds of problems?
It's actually quite adept. It can detect both direct insulation failures, like a breakdown, and maybe more importantly, it can spot the conditions that are likely to lead to failure down the line. And it can do this even in electrically noisy environments, like near power converters.
So what's the key signal for insulation health?
A really key indicator is what's known as the winding stress signature. This appears at specific frequencies related to the main electrical frequency, the number of pole pairs in the generator, and the slip, that difference in speed between the rotor and the rotating magnetic field. It used to be thought this just indicated turn-to-turn shorts, but now it's better understood as indicating energy discharge between adjacent turns in the windings. Things like partial discharge, which is a slow degradation process, especially common with the high-frequency voltages from modern inverters.
Are there other electrical signs pointing to insulation trouble?
Oh, absolutely. We also look closely at stator slot frequencies and their harmonics. If the levels of these frequencies get high, it can indicate movement of the coils within the stator slots or maybe the presence of actual turn-to-turn shorts. If the decibel levels get really high, it can even indicate electrical noise or sparking.
What about failure to ground?
Yeah, in cases where the insulation breaks down so badly that it creates a path to ground, you can sometimes see evidence of that in the ground conductors of the system. The frequency spectrum in the ground wire might even start to mirror the line frequency spectrum. Also, a big warning sign for general insulation deterioration is the appearance of sideband frequencies around the mainline frequency, specifically at plus or minus 15 hertz.
15 hertz sidebands. Okay.
Yeah, especially if you see that along with the winding stress signature and those other stator-related signals, it's often a strong indicator things are degrading. And if you can't directly measure ground current, sometimes you can use induction coils, clamp on sensors, basically around the ground cables to get an estimate of the current flow and its frequency content, then compare that to the line current signature.
So summing up the MCSA part for windings.
Okay, so MCSA methods specifically can help spot turn shorts, often showing up as winding stress first, then later stage stator defects. Insulation to ground problems, you look for those plus minus 15 hertz sidebands, stator defects, maybe that mirrored ground current. And general winding degradation, maybe from contamination or moisture getting in, often shows a combination of the 15 hertz sidebands, winding stress, stator defects, and ground current issues.
And the papers had examples of this.
Yeah, the case studies were quite compelling. They showed detecting winding stress and ground leakage using these methods on test rigs, and the findings were later confirmed by physically inspecting the motors and doing traditional electrical tests like surge testing. It really backs up the technique's validity.
That's a really fascinating look at how ESA MCSA acts like an electrical stethoscope for the turbine's insides. Now, one of the papers also went into quite a bit of detail about nacelle circulating currents. What exactly are those and why are they a concern?
Right, circulating currents. These are basically stray electrical currents flowing in loops within the wind turbine's nacelle. That's the main housing up top holding the generator, gearbox, etc. And they can have a surprisingly wide-ranging negative impact.
How so?
They can affect the main transformer, the generator's insulation, and definitely its bearings, the gearbox bearings and gears, the main bearings we already discussed, and even the sensitive power electronics. The research we looked at focused mainly on asynchronous DFIs and standard induction generators.
And the impact is significant.
The statistics quoted are pretty eye-opening. Up to 60% of generator bearing failures might be linked to them. Potentially a third to a half of stator winding failures could be due to these currents finding unintended paths to ground. We already mentioned the gearbox numbers around 76% of bearing and 17% of gear failures. And up to 60% of main bearing failures show evidence suggesting circulating currents played a role.
Wow, those numbers keep coming up. It connects a lot of dots.
It really does. And given the huge cost of replacing any of those major components, finding ways to detect and mitigate these currents early is obviously a huge priority.
So where do these currents come from? And how do the researchers study them?
Well, the sources described a detailed multi-year study. They basically went into operational wind turbines and mapped out where these currents were flowing. They also tested different mitigation strategies like special ground filtering and shaft grounding brushes.
And what do they find?
They found significant circulating currents up in the nacelle, mostly at the generator's operating frequency. But interestingly, as you measure further down the power, the dominant frequency of these stray currents tends to shift to the grid frequency, like 60 hertz, which is the output frequency of the power converter down below.
And the amount of current?
The magnitudes were surprisingly high. They measured up to 150 amps peak on the main bearing ground path in one case, even with mitigation in place. Other spots showed over 30 amps up tower and over 50 amps near the tower base.
150 amps through a bearing ground. That sounds like a lot.
It is. What's also really significant is the presence of high-frequency noise or components in these current waveforms, sometimes extending way up, even to 22 kilohertz, well beyond the normal power frequencies.
High frequencies, like from the power electronics.
Likely related, yes. To try and understand the potential damage from these high-frequency hits, they developed a metric called the Relative Harm Index, or RHI.
Okay, relative harm index. How does that help?
The RHI basically quantifies the potential for damage based on how much energy is in those higher frequencies compared to the main 50 or 60 hertz component. It uses a logarithmic scale, so a higher positive RHI value suggests a greater potential for harm, like electrical discharge damage.
Can you give an example?
Yeah. In one case, they saw a high-frequency peak around 5 kilohertz that measured at angst 18 dB relative to the main frequency. That translated to an RHI of about 3. Their scale suggests this indicates severe electrical discharge activity, something needing immediate attention.
And they linked current levels to damage.
They did. The study proposed ranges like under 10 amps peak ground, current being mild, 1050 amps moderate, 5100 severe, and over 100 amps extreme in terms of potential bearing damage. So that 150 amp peak measured across the main bearing ground, even with a grounding brush supposedly installed, clearly indicated a severe condition.
So the brush wasn't fully working.
Well, it highlights a key issue. Current divides based on impedance. The current will split between the bearing itself and the grounding brush path. The formula is basically I bearing, I total, Z brush, Z bearing plus Z brush. The problem is impedance Z changes with frequency, so a brush might offer a good path at 60 hertz, but at higher frequencies, its impedance might rise, and more current could be forced through the bearing instead.
Ah, I see. So the high frequencies are harder to divert.
Exactly. The overall conclusion from this research was pretty clear. Standard grounding systems in turbines are mostly designed for lightning protection. They aren't always effective at handling these AC circulating currents, and especially the high-frequency noise generated up in the nacelle. Right now, the best solutions usually involve electrical isolation, like insulated bearings, insulated mountings combined with shaft grounding brushes. But even those have limitations, especially when the currents get really high.
This really paints a picture of just how complex managing the electrical environment inside these huge machines actually is. Okay, to kind of bring this all together, what are the main overarching benefits of using ESA MCSA as part of a maintenance strategy for these DFIG turbines?
Well, at the end of the day, ESA and MCSA provide incredibly valuable tools for predicting failures, both electrical and mechanical, within the wind turbine generator and its whole powertrain. That unique aspect of the air gap magnetic field acting as this natural transducer lets us assess the health of many different components all at once from one measurement point.
That's a key advantage.
It really is. And the enhanced resolution of modern instruments, as we discussed, is absolutely essential for telling apart those closely spaced fault frequencies you find in these complex variable speed systems. These techniques can also help us understand how different problems might be interacting with each other.
Like a bearing issue causing stress elsewhere.
Exactly. And they can be instrumental in doing proper root cause analysis when something does fail, but maybe the most significant advantage, certainly from an owner's perspective, is the potential for really substantial reductions in both operational costs and turbine downtime.
How so?
Through that early detection of problems, it allows for proactive planned maintenance instead of reactive emergency repairs, and it often means you can perform less costly repairs up tower, avoiding those huge expenses associated with major component replacements.
So we've taken a really deep dive today into the reliability challenges of DFIG wind turbines and how MCSA really functions as this critical diagnostic toolkit. It seems pretty clear that having a solid grasp of these techniques is, well, essential for anyone involved in wind energy operations, maintenance, asset management, you name it.
Absolutely. By continuously listening to the electrical signatures of these turbines, we can significantly improve their operational efficiency, potentially extend their working lifespan, and ultimately contribute to a more reliable and sustainable energy future.
Right. And on that note, here's maybe a final thought for you, the listener. As our reliance on wind energy keeps growing, how do you think further innovations in monitoring tech like MCSA will shape the future? How will they help optimize turbine performance even more and accelerate our transition towards that cleaner energy landscape? Something to think about. We definitely encourage you to explore the research we touched on today and delve further into this ever-evolving world of wind turbine technology. Thanks for joining us on this deep dive.